So, welcome to our second live boundary layer session. Just a couple of reminders before we get started. You are muted and you are not able to unmute yourself until after Dylan concludes and is ready for questions. So just stay muted. I will go ahead and do the introduction here just to keep it simple for muting and unmuting. Once questions are open, I will remove the permission and you'll be able to unmute yourself to ask questions. Just please do be considerate and try not to talk over each other if somebody else is asking a question. Also, a reminder to mute yourself once you're done asking a question, just so it's easy for everybody else to hear when Dylan speaks. If you have the internet bandwidth and feel comfortable doing so, do consider leaving your video on. I'll be leaving my video on. It's awkward to give a seminar to an empty room, so I think the video in the little corner can sometimes be helpful to see smiling faces. So that's up to you, not a requirement. If your bandwidth does start to fail and you start having a hard time hearing, do stop your video. And my phone number is in the chat. If you get kicked out and for some reason can't get back in, feel free to send me a text message. As a reminder, this is recorded. The recording's already started for the seminar itself, and the Q&A session will also be recorded and later uploaded to our YouTube channel so that the rest of our community can hear some of the interesting stuff that Dylan's working on. And finally, just a quick reminder for students enrolled in this class, you are still expected to fill out the peer review form, so that link is still available online in the syllabus. So do take a look there and let me know if you have any questions. So today our speaker is PhD candidate Dylan Reif. Dylan became interested in meteorology from an early age. In the May 3rd, 1999 tornado only solidified that interest in meteorology. Dylan graduated with his bachelor's degree from OU in May of 2013 and got his master's degree from OU in 2015 working with Howie Bluestein on nocturnal convection. He has extensive fieldwork experience. In 2015, he participated in the PECAN field project, and since 2016 has been the operator and navigator of the RaXPol Doppler radar. Today, Dylan will be speaking on initiation mechanisms of nocturnal convection without nearby surface boundaries. And with that, I'll leave it to Dylan.
Alrighty, thanks, Liz. Hopefully my audio is still working. Otherwise, it'd be a very awkward seminar. But today I'm going to be presenting my PhD update, and I'm basically focusing on initiation mechanisms of nocturnal convection, specifically over the Great Plains, without any type of surface forcing. Yeah, there we go. Okay, so nocturnal convection is common over the central and southern Great Plains during the late spring and summer months, and this nocturnal maximum of precipitation was one of the reasons for the PECAN field project. On this figure I have shown here, we have average radar echo frequency. Basically, this is precipitation as a function of longitude and time, and we can see here that precipitation usually occurs at a maximum in the lee of the Rockies around 0Z, so late afternoon. And then it propagates eastward throughout the domain during the nighttime here, and we get this resultant nocturnal maximum in precipitation over the Oklahoma and Arkansas longitudes between about 6 and 12 UTC. And so up to 70% of that precipitation is attributed to events that initiate in the lee of the Rockies. The rest of that precipitation can be attributed to convection that initiates over the plains. And for my master's work, I formulated a 20-year climatology of nocturnal convection initiation, where we had three primary types of convection that we identified. Storms that form on surface boundaries, storms that form on the cold side of surface boundaries, and storms that form without any type of clear surface forcing, what are referred to here as the no boundary CI group. And that's going to be the focus of this presentation. So again, my 20-year climatology, which was my master's work, we identified this as what we call the no boundary CI mode, or NBCI mode. And there have been studies that focus on this pristine initiation without surface boundaries. And in all of these studies, there have been some common initiation features. And these include atmospheric gravity waves, the nocturnal low-level jet, and PV anomalies. And I want to emphasize that this is not an inclusive list. There are a lot of different types of ways that these storms can form, but these three appear to be some of the most common. So that brings me to the outline of this talk. I'm going to review each of those three initiation mechanisms, specifically how they can result in CI without surface forcings. Then I'm going to talk about how I'm going to study these forcings, and it's going to be a combination of idealized numerical simulations and PV inversion. Then I'm going to show some of the results that I've got so far, which will lead me into my current and future work. So to start off, let's talk about atmospheric gravity waves. There are many kinds of gravity waves in the atmosphere. These range from deep tropospheric gravity waves that usually spawn outside of and ahead of big, large convective systems, inertia gravity waves, and these lower tropospheric gravity waves. And we're going to focus on the lower tropospheric gravity waves and, to an extent, atmospheric bores, because these types of gravity waves have been associated with this pristine nocturnal CI more than the other kinds. And the figure I have shown here on the right just kind of illustrates this initiation mechanism for one really specific case involving gravity waves. And we observed this during PECAN. We have this gravity wave that was between 1.5 and 3 kilometers above the ground. And the crests of the waves and the rising motion was able to get into this area of relatively low SEN, enough to lift parcels to their LFC. And this was really tough to observe, but we had, fortunately during PECAN, a lot of observation platforms where we could actually see this occur. So atmospheric bores are a subset of gravity waves, and they're usually created ahead of density currents, as that density current will interact with the stable layer near the surface and the curvature of the wind shear, especially in the lowest kilometer. These atmospheric bores can lift air parcels to their LFC because they result in layer lifting and can be about 500 meters to even as much as 2 kilometers above the ground. Now, how are atmospheric bores created that we care about in this case? Well, a lot of times you have a pre-existing convective system over the Great Plains. That convective system is then going to generate a density current. And during the nighttime, that density current is going to start propagating, and the interaction of that density current with the nocturnal stable layer and the curvature of the low-level wind shear will generate an atmospheric bore that then propagates out ahead of that density current. And then sometimes that pre-existing convective system can decay, the density current can no longer exist sometimes, and then we have the atmospheric bore that just is there by itself. Here's an illustration of just vertically pointing data. The top panel is vertical velocity. Note that the magnitude here is about 1 plus or minus 1 meter per second. This is common with atmospheric bores, though we have observed vertical velocities of greater than 6 meters per second. Really, the most important part here is this net displacement of the nocturnal boundary layer depth, and we can see this in the mixing ratio. We have about a 500 meter displacement in the vertical for these air parcels as they interact with this atmospheric bore. And so that lift enough can be enough to initiate convection. And so once we get past atmospheric bores for initiation mechanisms, we can talk about the nocturnal low-level jet. This is a common low-level wind maximum at night over the Great Plains. The speed maximum is usually less than 1 kilometer above the ground, and is commonly less than 500 meters above the ground. Now, this relates to this study because 74% of the storms that initiated without clear surface forcing in that 20-year climatology were associated with some kind of low-level jet. This isn't surprising, as this is a common feature at night over the plains. But what is really interesting, though, is that the linear systems in this mode tended to be oriented north-south, and they tended to form on the eastern side of the low-level jet. Here's a figure from that study, and 3/4 of the events actually formed on the eastern side of the jet, which was actually very surprising. But it does correspond pretty well with some of the studies that have occurred in the last few years. Specifically, Josh Gebauer's heterogeneous low-level jet study. And so on this slide, I've illustrated some initiation mechanisms for the low-level jet that we're actually not going to be focusing on this study. And those include isentropic applied, which is basically going to be air moves up and over a quasi-stationary front, initiates convection on the cold side of the front. We're also not going to be concerned with speed convergence at the terminus of the low-level jet. And while this is an important one here, we're not going to be concerned about convergence associated with a heterogeneous low-level jet, as Josh is already studying that. And this is going to be a north-south oriented convergence zone that forms on the eastern side. And here's a schematic here showing that. Easterlies on the eastern side of the domain, and the varying winds associated with the low-level jet will cause this convergence zone. So what are we going to be focusing on? We're going to actually focus on a different type of ascent. This is a broad mesoscale ascent that Alan Shapiro showed in his paper a couple years ago. The ascent is located above the center of a maximum and horizontally varying buoyancy field, which I've shown here. And here's the corresponding potential temperature field associated with that buoyancy gradient. The magnitude of this ascent is usually between 3 and 10 centimeters per second. Now, this doesn't seem very strong, but sustained over a period of 6 to 8 hours can result in pretty significant vertical displacement of air parcels. The maximum usually occurs a few hours after the development of the jet, and the static stability in the free atmosphere does affect the magnitude of the vertical velocity. The stronger that stability, the weaker the ascent is going to be. And just here's a little snippet from that paper. Specifically, I want to emphasize this. Alan Shapiro did an analytical model of this, but what is kind of missing at this point is a more, as he said, a more rigorous exploration of this theory. And that's what we're going to be trying to do in our study. And I will discuss the results from that, how I set the model up for that in just a bit. But that's the ascent that we're going to focus on. Finally, the last type of initiation mechanism that I'm going to focus on is initiation associated with PV anomalies. Now, the eastward propagation of these PV anomalies over the Great Plains and the eastward propagation of that nocturnal rainfall have been shown to have a similar phase. And there's been an argument that these PV anomalies are responsible for at least a portion of this nocturnal precipitation maximum. It's not surprising because PV anomalies can be created by diabatic forcings, and a lot of times convective systems are associated with very strong diabatic forcings. So it's not surprised that they have similar phase. The figure here just shows a schematic, just to get us on the same page, of what the isentropes, which are these solid contours here, they're all solid contours, but these horizontal-ish solid contours, and the circulation, the cyclonic circulation associated with a cyclonic PV anomaly. That's these here, these are corresponding wind speeds. However, we're associated with these PV anomalies, whether or not we actually can get a ascent that is enough for CI is really kind of yet to be determined. We're not really sure exactly if these PV anomalies can initiate convection by themselves. We know that they are associated with ascent, and if they're in the sweet spot, it could initiate convection, but that's what we're going to test. Shown here on the bottom of this panel is a schematic of a cyclonic PV anomaly, and where you can get ascent is on the down shear side of these PV anomalies. Now, whether or not the ascent is going to be on the northern half of that down shear side or the southern half of that down shear side depends a lot on the PV anomaly itself. It depends a lot on the wind field, and it depends on, and the net displacement of parcels is going to be dependent on how long they reside near the PV anomaly itself. So there's a lot of ifs here about whether or not we can get ascent here, but we're going to try, and we're going to see what we can do. So that just kind of hopefully is going to get us all on the same page for our initiation mechanisms. Now I'm going to actually test the mechanisms, and I'm going to illustrate how I'm going to do that right here. So as I mentioned before, I'm going to use two methods. The first is using Cloud Model 1, which is an idealized numerical model that was developed by George Bryan as part of his PhD work at Penn State. He's helped me quite a bit on getting this set up. And the second one is a PV inversion technique. And this was really pioneered and made popular with Hoskins et al. In 1985, who discussed that you can invert the flow around a PV field And Chris Davis and Kerry Emanuel published a paper that illustrated this technique. But in order to do this, first we need some type of atmosphere. And in that 20-year climatology, I have more than 100 cases of this no boundary CI mode. And I've taken proximity soundings for most of those cases, and I've averaged them together and composited them together into one idealized sounding here. And important features to note about this sounding is we have this low-level stable layer near the surface below 900 hectopascals. We have this, if you squint really hard, you can see a lower to mid-tropospheric moisture maximum, and we initialize with a low-level jet. Note that these winds are in meters per second. And so while this might seem like a weak low-level jet, remember that this is an average of more than 100 events. So it's not surprising that we're getting a little bit of a weak jet. But the direction is in the exact sense that we would expect. So then what we do is, because we have an average of over 100 events, we can actually create probability density functions for each variable at each height level. And what we want to do is we want to see how representative this number is to that specific level. And what I've shown here are different violin plots. And these are, if you ignore the bottom half, this is a probability density function of, for example, this is temperature here, dew point, potential temperature, and d theta dz. And we can see that for the most part, we have some type of Gaussian-like distribution. And so when we have Gaussian-like distributions, we can start looking at standard deviations. So I've picked 4 variables here. This plot is potential temperature. This is d theta dz. This is the u component of the wind. And this is the v component of the wind. And what we can do is overlay these probability density functions onto that graph. And this is what they look like. So for temperature, we can see most of the line, most of these solid red. And the more solid the red, the more closer you are to this peak. So that's the darkest red. And the line corresponds pretty well. For d theta dz, again, it corresponds pretty well. We do have this offset. There's a lot of variation in the lower atmosphere, though. And for U and wind, we're kind of smeared out more horizontally. But these are all fairly Gaussian-like distributions. So what can we do? Well, we can actually start to create a parameter space of different environments to look at. So what I have shown here on this blue line is the average quantity for these variables. This is theta, d theta dz, u component of, oh, this is, sorry, temperature, my bad. Temperature, d theta dz, u, and v. And the blue line is the average, is what's shown on the sounding. This orange line, or yellowish orangish line here, is the +1 standard deviation value for that parameter. The green line is the -1 standard deviation. So this should account for most of the typical range that we'd see for these environments. What I want to point out here is if we just take a look at this temperature field, using a ±1 standard deviation atmosphere has the effect of just shifting this profile left and right. We don't really change the stability. We don't really change any of the other parameters that we care about. And we're really focused on stability in this case. So what we're going to do is we're going to take that d theta dz and recalculate the temperature and potential temperature based on that d theta dz standard deviations. And so on this plot here, on this left-hand side, I just show the temperature shifted and potential temperature calculated from that. On this right side, I show the potential temperature that's calculated from a ±1 sigma d theta dz, and then the recomputed temperature. And so we can see quite a bit of variation between these two sides. And the right side is really what we want. So in a sense, we have a ±1 standard deviation lapse rate. So when I say like weak temperature and stuff in the future slides, it's really referring to temperature computed from the lapse rate. Okay, so that's kind of a lot. So what does that give us? So we start with the base sounding, this ATAW, which means average temperature, average wind environment. That's just created from the average. Then what we have is we have this parameter space of 9 different environments. And I haven't shown all the acronyms here because there's a whole lot. But do note that WTWW stands for weak temperature, weak wind. That's basically the -1 standard deviation temperature, the -1 standard deviation winds. And then we go all the way to strong temperature, strong winds, which is the +1 standard deviation temperature, the +1 standard deviation winds. And so now we have this 9 different environments of typical values that we can look at for these no boundary CI events to see how each of the mechanisms affect each of these different environments. Okay, so now I've gotten all of that out of the way, let's actually start looking at the results and model setups for all of the 3 different initiation mechanisms. We'll start with gravity waves. So our objective here is to identify the effect that the passage of a gravity wave or an atmospheric bore, again, in terms of a parcel's net vertical displacement throughout the night, has on these environments. So here's the model setup. I use CM1. I have horizontal grid spacings of 500 meters. I have a vertical grid spacing of 25 meters below 2 kilometers, which is stretched vertically to 650 meters at about 15 kilometers. I have 1,500 horizontal grid points and 120 vertical grid points. And the input soundings are based on the environments and their ±1 standard deviation parameter space stuff that we showed on the last couple of slides. In this simulation, there's no boundary layer scheme, there's no radiation scheme. I have open boundary conditions. And this is a dry simulation, and this is in fact a 3-dimensional simulation. So how can I generate an atmospheric bore? Well, the first is a statically stable atmosphere and curvature of the wind profile. And these have the effect of, especially the curvature of the wind profile, of having the score parameter decrease as a function of height, which is a necessary condition for wave trapping. And the density current is going to be needed because I need to have a density current that interacts with the stable layer and that curvature of the wind profile in order to generate the gravity wave. Now, all of these are essentially satisfied with that environment that we've created from the sounding. But I do need to add a density current to the simulation. And luckily for me, I have plenty of experience adding density currents to CM1. So to do that, we're going to create a circular cold pool with a 5-kilometer diameter. The magnitude of theta prime is 8 Kelvin at the surface, negative because we're cold. And that magnitude decreases to 0, 1 kilometer above the ground with this sinusoidal weighted function that I have here. The wind in this case is southerly. My initial conditions are horizontally homogeneous. So the most favored bore location is going to be along the -y direction, located at x = 0. And so I'm going to show some early simulation results. This plot is basically just to show you that this is in fact a 3-dimensional simulation. Here's the weak temperature, weak wind plot. This is the average temperature, average wind, strong temperature, strong winds. So the lapse rate basically increases from top to bottom, and the winds increase from left to right. That's the best way to think of these plots, and I have these plots for most of these variables. Color filled here is potential temperature perturbation, and this is at the lowest model level. Again, the only point I want to make on this slide is really just to show you that these are in fact 3-dimensional simulations. And so on the next few slides, I'm going to show cross sections, and these cross sections are going to be taken along these black lines here. I guess they're green now, they changed something. But so now I'm going to actually show the cross sections. Contoured here is potential temperature, dang it. And color filled, especially on the next couple of slides, is going to be vertical velocity. So this is at time t = 0. And so there's actually not much in the way of vertical velocity at the moment. But if we look at time t equals basically an hour and a half after the simulation, along the top row, this is the weak temperature, so basically neutrally stratified environment. We just see a density current. We don't really see any type of gravity wave response out ahead of it. However, in this middle panel, this is the average temperature or average lapse rate for the nocturnal environments. We do start to see evidence of these gravity waves out ahead of this density current. You can see the density current is located down here. And same thing with the strong lapse rate environments. if we look even farther out, this is time t equals 3 hours into the simulation, we start to see evidence of a very well-defined gravity wave, especially in this middle panel. It's not as evident here in the bottom panel, but there is still evidence of a gravity wave in those simulations as well. And so I admittedly haven't done a whole heck of a lot with these simulations up until this point because I've been focusing on the other two stuff that I'll show. But now that I've got these simulations and I've got a gravity wave in there, I can start to analyze the net displacement of parcels as the wave passes through them. And what we can do is initialize these environments with passive tracers. And I can put as many passive tracers at whatever levels that I want. And so that's going to be the plan on how I do that. I do have to wait a certain amount of time after the model simulation starts to get away from the center portion where that density current and the cold pull collapses in on itself, because there's a lot of extraneous stuff there that I need to get away from. But the rest of it looks pretty good. Okay, so the next part is going to be the low-level jet. And we're going to identify, again, our goal is to identify the effect that ascent above the jet has in terms of the net displacement on these typical no boundary events. And so this is the model setup for these type of simulations. My horizontal grid spacing is 4,000 meters or 4 kilometers. My vertical grid spacing again is 25 meters below 4 kilometers, stretched to 450 meters at about 18 kilometers. And this has 300 horizontal grid points, 220 vertical grid points. And the input sounding is based on the environments that we've shown previously again. The difference, really the biggest difference between this simulation and the gravity wave simulation is I run these with full physics because I need to simulate one diurnal cycle. And CM1 really only has one boundary layer scheme. That's the YSU scheme, so that's why I'm using that. I have the RRTNG radiation scheme. I have open boundary conditions. And this is a quote-unquote dry simulation. And the reason I put quotation marks around the word dry is because I have a radiation scheme turned on, I have to have a microphysics scheme turned on. In this case, in case you're curious, it's the Morrison double moment microphysics scheme. But what I've done is I have removed all moisture from the environment. So it is effectively still a dry simulation, even though I have a microphysics scheme turned on. And to keep this simple, we're running this with no terrain. Realistically, we should have terrain, but that's going to complicate model setups. But we can still get the same job done without terrain. So how do I generate a jet? Well, generating the low-level jet itself is actually pretty straightforward. As turbulent mixing from the daytime shuts off, and we have that from the radiation scheme, an inertial oscillation is created and the wind starts to accelerate. Now, I have no problems generating a low-level jet in these simulations. However, I have had issues generating ascent above the jets. But recently, within the last few days, especially with meeting with Alan Shapiro, I have actually had success generating the mesoscale ascent that we've been trying to get. But do note, since I've only done this in the last few days, the simulations here shown are very preliminary, and I have not really examined them too much. But I'm very excited that it actually works for once. So because we're dealing with a horizontal buoyancy gradient for the low-level jet simulations, I actually have to create that horizontal buoyancy gradient in the model. And while I can't change the buoyancy variable itself, I can actually change the potential temperature field. And so what I've done is I've put a heating pad at the surface. And I can change the magnitude of this heating pad however I'd like, but I do want to generate just a couple of degrees of horizontal potential temperature gradient throughout the course of a day. So I do this by putting a sinusoidal variation in that heating as a function of space, shown here. And I also put a weighting function as a function of time of day. And so I have a maximum, I allow a maximum heating right about noon, decreases to 0 at sunset, and remains to 0 throughout the night. And the whole point of this is to generate a relatively smooth field for heating rate. I don't want any type of sudden shutoffs for heating, which could create some discontinuities. And so this is what that heating looks like as a function of time, which increases from top to bottom, and space on the ordinate, or on the x-axis. And so we can see the maximum heating occurs, this is time since sunrise, so it occurs right about noon, right in the middle of the domain. So let's just see what the low-level jet simulation looks like itself. And so this is just time t equals 0. I initialize the model with the jet itself. And as the day progresses, we get the heating of the atmosphere, which we turn into a well-mixed atmosphere. And the heating maximizes during the daytime, and the jet then redevelops during the course of the night. And note that the jet is stronger than the day before. That's okay. And so the biggest question we have is, first, is this actually a low-level jet? Well, let's take a look at a photograph. What we should see is an inertial oscillation of the, and this is what I'm really excited about. So during the daytime, we get the boundary layer growth. And at night, when the turbulent emission shuts off, we have this sustained region of mesoscale ascent that's right in the center of the domain, which is right where I put that maximum in horizontal buoyancy, or in the maximum of heating. And it's the magnitude here is weaker than what Alan Shapiro had in his analytical model, but not by a whole heck of a lot. And it is sustained throughout the night. And again, I haven't looked at this too much because I finally got this stuff to work, and this has taken me quite a long time. But I will eventually be able to proceed with the analysis for this. So what I've been really excited about, again, is just getting this to work and being able to move on with this stuff. Okay, so after the low-level jet, we have just one more thing I want to talk about, and that's PV inversion. And so I will start with the 3 ellipses here, because this is actually quite a complicated problem. And so it is a useful technique that we can use to back out the wind field and potential temperature field associated with PV anomalies. And again, this technique works because under most conditions that we deal with, adiabatic and frictionless, we have a conserved quantity. As long as we have knowledge of the wind field and the theta field, at some points we can actually identify the total field. So I'm going to throw up a whole bunch of equations here because I really want to describe how this works. So first, we recall an equation for PV in terms of the geopotential phi and the stream function psi. And that looks like this. It's really, really pleasant looking. And then we need some type of balance condition. And because we deal with circularly symmetric PV anomalies for the most part, we can employ the Charney 1957 balance condition, which I've reproduced here. And so again, these are really, really lovely equations. So again, let's talk about how this works. Let's take this equation here, and we're going to solve it for this function grad squared psi. And that looks like this. And then when we recall our balance equation, we effectively have 2 equations and 2 unknowns. We know the PV field. This is pressure, gravity, kappa is just 2/7. Pi is the Exner function in this case, so we're using pi as a vertical coordinate. This is just Coriolis parameter. We just don't know phi, we don't know psi. So we have those equations, and we're not quite done yet. We need some type of boundary conditions. And depending on your perspective, this is either a bad thing or a good thing if you really like boundary conditions. So for the lateral boundary conditions, especially for the stream function, I'm employing Neumann conditions, which is 0 flux along the edge of the domain. For the geopotential, I'm implying Dirichlet conditions, which I've basically locked to be the initial value. The upper and lower boundary conditions are also, oh, I misspelled that, Neumann conditions, and we're applying a constant flux, and it's given by this. So the process is the process to solve the system of equations is iteration. And I will skip that slide and I will just describe it here. What we're going to do is we have an initial guess of our geopotential and our stream function. We put that throughout the domain, and we lock the lateral boundary conditions based on what we employ. We take that first guess for the stream function, and we put it into this equation here, and we solve this and use a Poisson solver with the appropriate boundary conditions to back out the new geopotential. And that represents what I'm going to call minor iterations. So the minor iteration is to solve the Poisson operator. Then we take that value for the geopotential and we plug it into this equation up on top using the previous value for the stream function. Then we have that field and we solve that Poisson operator for the stream function. And that process of getting the updated psi represents one major iteration. So then we take that updated psi, put it back into here, and update the geopotential, put that back up in there, and use the previous value of psi to update the new psi. And we keep doing that over and over again until the system converges. Now, that's basically it. It's really simple. It's really not that simple. The problem is the convergence condition, when this stops, depends on the magnitude of the anomaly, how smooth it is, to some extent its shape, and the grid spacing. And the boundary conditions and the initial input can be tough, and those in a way affect the solution. And I've tried different types of boundary conditions, and I finally come up with the best set that works for most cases. Again, it does actually seem to work pretty well, and I'll show the results here in just a second, though the parameters do need to be tuned for case-by-case basis. It also seems to struggle with small grid spacing, and by small grid spacing, I mean less than about 5 kilometers horizontal. My computer tends to run out of memory when I try to invert the field of stuff smaller than that, so I don't actually know if it's working or not for that, but I just know it crashes my computers. But it does work for everything else, so I'm going to assume it works if I let it go for weeks. I'm going to show an example real quick. This is just a 2.2, roughly, idealized PV anomaly, again, embedded in the full field of PV, centered at about 5 kilometers above the ground. The horizontal width of the anomaly is pretty large. I set it to be 500 kilometers. Do note that the size of the anomaly and where I put it is a bit arbitrary. This is mostly a proof of concept at the moment. And so the panel on the left here is my initial PV field. This is my horizontal extent. The y-axis is my vertical, so right at 5 kilometers. We have this 2.2 PVU anomaly that's centered in the field. And so then I take the PV inversion technique, I invert the flow field around it, and I obtain this result here. So I get a cyclone around the PV. That's sanity check 1. And I get the isentropes to bend inward towards the anomaly in about the right shape. That's sanity check number 2. So the question is this right? We have a product of 2 variables with PV. We have a product of vorticity and of d theta dz. And so it's kind of tough to determine whether or not we actually have one that's correct. So what you can do is we can recalculate PV based on the inverted field and see how close it is to the original field. And that's what I've done here. Just to recall, this is the initial field, and this is the recomputed PV field based on this. I had to make a couple of assumptions, especially with the vorticity, but otherwise it's not too bad. It's not perfect, but it's pretty close. And I'm constantly been updating this methodology to try to help account for this slight discrepancy. And I think a lot of this discrepancy has to do with numerics, has to do with how many major and minor iterations I do, and how much memory is on the computer for me to run the convergence condition out to smaller values. But again, it's close. And what it's going to let us do is actually diagnose a vertical motion associated with this PV anomaly around the field. And so that leads me to my ongoing work. I need to complete the low-level jet simulations now that I have and can generate ascent. Again, this is right now my highest priority objective. I need to actually analyze the net displacement of the air parcels for these 3 methods, or 3 mechanisms. I'm going to do this at different heights above the ground, just so we can see if we have this elevated convection at night. And if time permits, I'm going to combine different features. I'm going to superimpose a PV anomaly on top of my low-level jet simulations and see what the ascent looks like with that. I can do that upon the gravity wave simulations as well. I can add different streams of moisture and have horizontal temperature advection if I need to. that might be too much, but we'll see what we can do. And with that, I will finish here. I'd like to thank my advisor, Howie, and my committee members, Alan, Stephen, and Dave. I'd also like to thank Tammy Weckworth, Rich Fortuno, and George Bryan at NCAR for all of their help, and my former office mate, Zach, for his continued support emotionally throughout this project. And with that, I will stop talking for the second time.
Thanks, Dylan. So I went ahead and given you all permission now to unmute yourself, so you have the power. So if anybody has questions for Dylan, please go ahead and unmute yourself and ask away.
I have a question or two, but maybe I don't want to jinx us by starting off questioning about boundary conditions. So maybe someone else should go first. No? All right. Okay. Well, a few. I like the results on the your mesoscale heated the sine wave thing. They're starting to look interesting.
Yeah, it's about time, honestly.
So, but my questions actually concern the other stuff, the PV, the PV inversion. So these are nonlinear equations that you're working with. Both of them are nonlinear, and I'm not familiar with the original papers that derive these, but I'm a little concerned about the possibility for non-uniqueness in here. Have you tried using different first guesses and seeing that the results don't change?
I have tried to use different first guesses, yes, and the results are pretty similar between the two of them. They're not.
Okay, great.
I mean, they're not exactly the same because sometimes it takes a little bit longer to converge with some situations, but they're pretty close.
Okay. So now onto the boundary condition. Now in some of the some other problems, not this one, but I'm thinking about Galchen's thermodynamic retrieval, for example. In some cases, the boundary conditions are actually evident from the derivation that gives you the equation that you want to solve. In other words, when you get your PV conservation equation, but where did that come from? You had equations of motion to begin with. And if you follow the derivation of that, sometimes you can actually choose an intermediate equation in that derivation, and it tells you what the boundary condition is. Now that's the case in Galchen's thermodynamic retrieval. And I don't know if you've looked at that, maybe it's the case here as well. If it's something like that, then you actually don't have the freedom to specify, for example, your gradient of pressure on the boundary, but it tells you what it should be. And so in a way that's good because it removes a degree of freedom that you didn't know what to do with anyway. I don't know if you looked at that yet, or looked at that either with the potential vorticity one or the balance equation.
So I admittedly have not taken a look at that. The reason was because in the Chris Davis and Kerry Emanuel paper, they specify what boundary conditions that they used. And so I said, okay, I'm just going to try that. And I emailed Chris Davis, and that's basically what he told me to do. So I haven't looked at that, but I can just to see if it might make a difference.
Well, I'd recommend you at least take a look at it. The other reason I'm suggesting this, if you look at your initial PV plot and the final PV plot, and they do look similar somewhat. You know, there's areas where they differ, but the areas where they differ are outside, implying that it's the boundary condition that's having a factor there.
It's
if you notice the colors, they're actually different for the outside. Like you still get this, you know, near horizontal lines, but they're different values.
Yeah, so that is in part because I make really terrible figures, and I just realized that the contour intervals are different. Between these plots.
Okay. All right. So we withhold previous comment, but still urge you to take a look at the possibility that boundary conditions can emerge from your derivation of, say, the constant Q and the balance condition.
Yeah, I will attempt to look at that.
Okay, that's it for me.
All right, any other questions for Dylan from the group?
Dylan, Dave Parsons here. It's really great talk. I think for my own bias is that the jet dynamics perhaps are most likely to explain things that are forming to the right of the main jet axis, like in your earlier paper. For the gravity waves, they didn't quite look like bores to me. The maximum seemed a bit high, so I think one thing to check would be whether these simulations are actually in a partially blocked regime. And sometimes when you try to trigger, Ben Blake did some CM1 simulations a while ago, and when that cold pool was rather small, you were getting sort of flow around the cold pool, and it was triggering gravity waves and not really bores.
Yeah, so I have checked the parameter space for the partially blocked flow regime, and in all of the cases in the bottom two panels, the environment does fall within the partially blocked flow regime. Now, I do agree, and I need to do more testing to see what kind of gravity waves these are. They could be bores, they could be solitons, but I haven't admittedly looked too much at these because I've been trying to get the other stuff to work.
Yeah, and the other stuff might be more important in the end, but they don't really see the maximum W near the top of this table layer, things like that.